Okay, Bismillahirrahmanirrahim. Let's start with this one. We are now at CO5 of this course, and this CO5 is evaluate distinct adversarial search strategies and its algorithms. So, adversarial search strategies means competitive search strategies in which you are competing something with some other thing. So we have to see these strategies, and these strategies normally exist in games, and we will see some of its algorithm. We will study two algorithms in this CEO. So as I told you that adversarial search is about games, but what is adversarial search? So this is a kind of a definition for it, that when you have two or more players, when you are two or more players uh, competing with each other, and their goal is same, and when the goal is in conflict, in simple words, when two or more players are competing with each other and their goal is same, and every player wants to achieve that goal, then this is the environment of adversarial searches. So here you can see when two or more players with the conflicting goals, which means their goal is same and they are fighting for the same goal. So that's why conflicting goals. So when two or more players with the conflicting goals are trying to find the solution, to find that goal, huh? So then this is the environment of adversarial searches, and you can also call experience that are this kind of searches in games. And this environment, this adversarial environment, you can find in games. So now this is the problem definition for the game. This is the definition according to the AI that we study in chapter 2, maybe, or chapter 1, how we can define different problems by stating 5 different things, huh? So here we are defining those 5 different things for the problem definition of games. So a game is what? A game is also a search problem. And here we have to define its 5 things, and what is its initial state, players, action, result, terminal test, utility. So now it is becoming 6 points, not 5, but it's okay. So an S0, so all the games will have some initial state, And then so if you have any kind of a game, then you have to set up the starting state. You have to build the initial state. So every game must have some initial state, and then players. It can be 2 players, 3 players, whatever. Players into S. But here, what it means, player into S, the player that has the move, okay? If you have 2 players, at one time, one player is playing, and on other time, the other player is playing. So they have turns, huh? They have moves. So here, players into S means what? That which player has the move in state S. This S is for state S. So, or you can simply write it player, okay? And then you can write a sentence, how many players and how or which player has a move on state S. You can write in a sentence. Or you can simply say how many players you have in the game. Khalas. And then actions into S. So this S is a state again, and on this state, how many actions you can perform in the next level. If you are in a tree, if you are in a game tree, suppose, because you know that we can express all the searches into the form of tree. And if our game is also a search problem, then we can build a tree of that game. And if we can build a tree of that game, then in that tree there would be the nodes, and those nodes would be the states. And on each state, you will have further nodes, which means you have further actions on that state. So actions into S means what are the moves or what are the legal moves available at state S. And then result SA. So S is a state, A is the action. So when some player is playing at state S, maybe he's performing some action. So then on that state S, if some action A is performed, then where you reached after performing this action. This is the meaning of that. What is the result? When you perform this action A on this S, you will reach on the next state, maybe. So result from the state S with action A. And similarly, terminal test and the state S. On each state of the game, you will evaluate that state, that either that state is terminal state or not. Terminal means your game is over or not. So your game is over now or not at S. Okay, that is defined here. And then utility S comma P. This is something extra from those previous 5 things that you have studied in chapter 1 or 2. I don't remember. So here S is again state and P is for the player. So this utility S and P, normally you will use this utility function, or this is not a function, you can say when the game will reach at its terminal nodes, when the game will reach at its ending state S, then there would be some player at that state S, and that player would be P. Then you have to evaluate the utility value of that state. What would be the value of that state? You have to evaluate. This thing is representing, we are representing here with utility into S comma P. So this utility S into P will give us what? Final numeric value for a game. This will give us final value of the game that is ending in terminal state S for some player P. So when in the tree you will reach at the terminal nodes will have some value. This utility will return that value, and then that value will go up in the tree. Anyhow, this is the problem definition according to AI for the games. Now we are moving next. And here, so from that previous discussion, I intentionally spoken 3 or 4 times the word game tree, because that concept is connected with the search. So that's why now we are here at that point, game tree. So every game has the game tree. So previously we in this previous slide, we have studied initial state, actions, and the result. Those 3 things in the previous slide, those 3 things which are mentioned here again, if you have these 3 things, then you can design a game tree for any game. So these 3 things are necessary to design the game tree for any game. And if you will define the game tree, then here, for example, this is the node, this, all the blocks with the cells are nodes. And all these arrows, the links, these arrows representing moves. These arrows representing moves. So nodes are game states and edges are moves. And here we are going to take an example of a tic-tac-toe game. That is a simple game so that you can understand it easily. If we will take something like that, a game like that, then building a tree for that is not possible on this page. Okay. Even this for this tic-tac-toe, we cannot build the whole tree here. And if you will represent the whole tree, maybe it will be font will be too much smaller. Anyhow, so tic-tac-toe. And in this game, you normally uh, mark with some symbols. One symbol is X, other is O, or you can say this is cross and this is not. So other name for this game is cross or not, and crosses or something like that. So here we are starting where we don't have any mark here. It is empty here with the 9 cells. And here the player max has its move. This is one player max, this is another player min. This max has the move here, and initially this max has the option to mark this X at this place, or in the next cell, or in the next cell, or in the next cell in the lower row, or in the next. So these all are all the possibilities for marking this X for the player max. And then when it is done, so these are all the options. So that's why all options are opened. And now when the min player has this turn, then it has what? How many options left for the min? 3, 3, 6, 2, 8. 8 options. So it means after this node, you will have 8 for the nodes. So that's why here O min can mark O here, or in the next, or here, and so on, up to 8 nodes. Huh? And similarly, under this, the min player can mark eight different positions, mark at 8 different positions, and you can draw all those boxes here. Huh? Similarly for this one, similarly for this one, and so on. Now, after when the min player has taken his turn or taken his move, now how many options left for the max? 3, 3, 6, and 7. 7 options. So after this node, then max can mark at 7 different positions which you can design here. And similarly for others. And similarly for others. So, and now here when the max is done, again when the min has its move, then for the min, how many options you have? 6. So then under this node, you have 6 different options. Similarly for this, 6 different options, and so on. And in this way, you can go on. That's why here and so on is mentioned. And finally, we are representing some of the terminal nodes to get the understanding. Some of the terminal nodes to get the understanding. For example, if you will reach here, for example, if you reach here at this terminal node where you have 3 marks for the max and 3 marks for the min, and here min has this, you know what is tic-tac-toe. It is just making a row or a column or a diagonal, huh? So here the min player has these 3 values in a column or in a line, and the best value for the min is -1, or you can say utility value for the min player is -1, and the utility value for the max is +1. And if the game is drawn, then the value is 0. So here the min player is winning. So that's why this is the terminal state. And now the algorithm will calculate the utility value of this terminal state, and it would be -1. Similarly here, if you will see here, nobody is winning, huh? And the states are also complete. And here, so now here in this state, in this terminal state, the game is being drawn between the 2 players. And if you will look here at this terminal state, here the max player is winning. Hmm? The max player is winning. So that's why the algorithm will calculate the utility value of this terminal state, and it is +1. So from this game tree, for this simple example, you can imagine that it is not easy to build the game tree on a page for even a simple game, but all the games have the game tree because all the games are following some search strategy. But and this is the concept of the game tree. Now moving next, how in games we can make optimal decisions, how in games we can introduce something through which the algorithm will do a optimal decision on each state or whatever. So we want to follow some optimal strategy in games. Optimal strategy, you know what is the definition of optimal solution means? The best possible solution. Huh? So what is optimal strategy? This would be the strategy, or this would be some equation, this would be some formula, this would be something in the algorithm which will lead us to outcomes, which will give us some outcome at least as good as any other strategy in games. So when we will build this strategy, when we will introduce this equation or formula or whatever in the algorithm, this thing will give us the result which will be good as the other, as any other good equation can give us the result. Or in simply words, which will give us the result which would be the best possible solution, best possible result. You can say this thing in simple words. So normally, so we are going to discuss this thing with a simple concepts, and here we are going to take the concept of two-player games. When in a game you have only two players option, then these games would be called zero-sum games. The title for these games is zero-sum games, when only two players are there. And here in this game, and here in these games, zero-sum games, if one player is gaining, the other player is losing. Okay. If at some state one player is gaining, the other player is losing. So the gain of one player is balanced by the loss of another player in this category of games, in this category of games. For example, we have this equation. We are now taking a simple equation to understand the optimal strategy. And here we are using a static evaluation function, and we are calling it f of n. And here the definition of f of n is what? The complete row, column, diagonal, open positions for x. This is, we are discussing this for the tic-tac-toe, okay? Because that is a simple example. So complete row, column, diagonal, open positions for x minus complete RCD open positions for O. This is an equation which is written in theoretical form. What it means, we are going to understand this evaluation function here. For example, we are here where we have two x values and two O values. And now here O has done its move, and here we are marking what? Maybe x. X can mark how many positions? 3 and 2. X can mark in these positions, huh? So X can mark here, and then here, in the left open positions, and then here, and then here. These are the all possibilities after this node, huh? And now, if we will evaluate, if we will use this formula, static evaluation function f of n here, then what it means? Complete RCD open positions for x. It means x can make a line here, x can make a line here, 2, x can make a line here, 3, x can make a line here, 4. These are the open positions for the x. For the x. For the x, because first you have to write the open position for the x, and then you have to write the open position for the O. So this is 4, and here I am writing that 4, and then minus, and then open positions, and then, sorry. And then open positions for the O. Okay, O can mark a line here, or O can mark a line here, and there is no any other option. So only 2 options for the O. 4 options for the X, 2 options for the O, and when you will subtract, you will have the value 2 for this formula f of n. Similarly here, 1, 1, 2, 3, 4. It is again 4 for the X, and O has how many values? O has only 1 open position, you can say. So that's why 4 minus 1 is equal to 3. And here 1, 2, 3, and diagonal 4. This is 4. And open position for O, 1 and 2. That is 2 is equal to 2. Similarly, something here. Similarly, something here. So here we have calculated f of n for all of these options. And what it means, higher the value of f of n, higher the value of f of n, the closer the game is going to end. Or you can say, the closer you are going to win. If so, let's see that. Higher the value of f of n, if the value of the f of n that you calculated is higher, then what it means? It means you are closer the move towards a win. So the game is close to the winning position when the value of f of n is higher than the other moves. And if you will see here, I have pasted this picture again here so that I don't have to go back. So if you will see here, 3 is higher, 3 is higher, 3 is higher than the other existing values. So you have 3 moves. This is one move, this is another move, this is another move. So you have 3 moves with the value 3. So it means that these 3 moves are close, or in these 3 moves, game is close to the winning position. Winning position for the X or O, whatever. So, but if it is close to the winning position, but then you can assess that, okay, now Mark has taken its move. Now the move is for O. And O can do what? O can write O here to break this line, and then X can mark here, and then X will win in this position. In this position, X is 100% chance to win. And here, if you will see here, and if it is the move of the O can simply write or mark O here, and O can win. Here, X does not have any chance. And here, if you will see here, simply O can mark O here, and it can simply win. So here, X does not have any chance to win the game. So for the player X, if you can see, so the game is close to win when the f of n is higher. The game is close to the winning position, either for X, either for O. But we can say that here, the value of f of n is 3, but the player max, which is X, has only one possibility to win this game out of these 3 possibilities. So if you are considering more to the max player or the X player, then you can say this question is not good for me. So that, but this f of n is a simple equation. It's a simple equation, okay? But still it is useful, but it is a simple equation. But if you can build some more better equation, then you can get these results in a better way. In a better way. So this equation that we have presented here, or this evaluation function, or this heuristic function, you can say, this is a simple equation to get the understanding. You can build some more complex equations to 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 explore these different states further. And for that purpose, we are going to study an algorithm which is called minimax algorithm. Probably it is given here in this slide. We will start from here. So we are going to study a minimax algorithm. And in this algorithm, one word is mini, other is max, or min or max. It is again two-player game, huh? One player is min player, other is max player. But it is the name was given to these, due to these min and max terms, the name is given to this algorithm as minimax. And in this algorithm, one player is trying to minimize. Then if you are playing with the algorithm, then you are one player, algorithm is another player, okay? So if you are trying, and in this algorithm, if one player is trying to minimize the value, like min player, then the algorithm will try to maximize the value. And then it will create a two-player environment like that. So in the minimax algorithm, what are the different things which are existing in minimax algorithm? This algorithm deals only two players. One is maximizer, other is minimizer, or you can say max and min. Maximizer will try to maximize the value, positive value, and minimize will try to minimize the value. That is what we said, that one player, the gain of one player is exactly balanced by the loss of other player. And in this minimax algorithm, we will follow the depth first search. Okay, the depth first search. So that's why we can build a depth first search game tree for this algorithm if we want. And by using this depth first search, we will try to build a game tree from the root node up to the terminal nodes. And when you will reach at the terminal nodes, then you will calculate the value for that terminal node, and that value then you will propagate back up in the game tree up to the root to get the final value of the game, that's why it is written here value propagation. We will calculate terminal values, and then we will compare and then back propagated the values until the root node, okay? Let's see this minimax algorithm. So function, the name of the algorithm minimax, we are passing some node into it, state into it. Function minimax n is, okay, begin. We are starting from here, and then we are checking. Let's read it first so that you will understand. Whenever you are going to understand some algorithm, it is a technique to read it first. Either you are understanding or not, read it first, because then you will understand. After reading, you will have an idea what is the structure of the algorithm, where different things are lying. So anyhow, so we are passing n into it, and here then we are checking if n is deep nf. Here deep nf means if n is terminal node, okay? Deep nf means terminal node. Here deep nf means terminal nodes, because this is the maximum depth. So here if n is deep nf, if the condition is true, if n is a terminal node, if condition is true, then return the estimated score of this leaf. So if it is a terminal node, then calculate the utility value of this node and return that estimated or calculated value or score. Okay. Okay. If it is not a terminal node, then you will come into this else portion. And here, first you, if the node is n, then you are calculating, okay, let n1, n2, n3, and so on, nm are the successors of n. If n is a node, what are the next? For example, if n is a node, if this is n, what are the successors? 1, 2, and 3. These three nodes are the successors. So then you will say n1, n2, nm be the successors of that node. You will find what are the next neighboring nodes or successors, are the nodes which are coming next. What are those nodes? You will calculate and you will write it here. In this algorithm, you can say we are writing it here. So we are calculating what are the next successors or next nodes of this node n. After finding that, then we are finding if this our n node is a min node, which means if our n is a node for the min player, then we have this return statement, and then here we have a recursive call to this algorithm. Then we have the min, curly bracket starts, curly brackets ends, and this min means minimum in mathematics. Okay, this is not a min player. Okay, this min is not a min player. You can consider this min as a mathematical function which will give you the minimum value, the values. If you are giving some 4 or 5 different values to this function, it will give you the minimum. So you can say it is a min player because this is also the objective of the min player, to find the minimum. So anyhow, this is the min, this is a function which will give you the minimum value, and then you are calling minimax this algorithm. You are calling this algorithm again, minimax n1. N1 is the successor. Whatever the successor you have found here in this step, now you will apply this minimax. You will call this minimax algorithm for all of those successors. So you will apply minimax on n1, then you will apply minimax on an n2, and then you will apply minimax on an n3, and so on. You will apply minimax on nm, which are written here. Which are written here. So what is happening? For example, if this is the node, then you are applying this main function here, and main function here, and this is the curly bracket, you can say, curly brackets ends, and here you are applying the minimax algorithm again for this node, and then minimax here for this node, and so on for this node. This is what it means. This is what it means. And if your n is not a min node, then what it would be? It would be max node. Then you will come into the else portion. Then you will have this similar statement here, but with the max, not with the min. Return max, minimax n1, comma, minimax n2, comma, minimax n3, or whatever. So so for example, so if my n, for example, this one, if my this node n, if this is n, and this n is not a min node, it is a max node, then you will do what? You will apply max. You will apply this max is written here, curly brackets, And this max is written here. This max, curly bracket. And here for each of the nodes here, you will apply this minimax. You will apply this minimax. And this N1 is this node. Hmm? And similarly, you will apply this minimax here. And this N2 would be this node. Hmm? I hope that we have now got the understanding of this algorithm, not fully, but partially. What is the structure of the syntax? What is the structure of the algorithm? And after that, end minimax, which means this is the end of this algorithm. And now, now take this example. What? The screen? If the screen will come down, if I want to write something, I cannot.
No, just the half.
Okay. Is it okay for all of you? Hmm? Okay. So now I'm taking this example and I am running this example over this algorithm. So now my starting node is this one, which I am passing here in this minimax algorithm. And then I'm checking, and here the player max has the move. Okay, on this node, max has the move. Here the max has the move here on all, and then the min has the move, and this is the level of the min, or the layer of the min. And then next we will see. So here this node is going into it, and then I'm checking this node is deep enough, this node is terminal. No, it is not, it is the root. It is the root node, huh? So then this condition is false, and I am going directly to this else portion. And here I am calculating what are the successors. This one, and this one are the successors. And I am calling them N1, N2, and N3. So I have now found this step is now done. And here I'm now checking this condition. If n is a min node, what is n? This is n. Initially, this is my n. So if n is a min node, this n is a min node? No, it is not. It is max node. It is max node. So then I will come into this else portion, and here I will execute this statement, return. Return max. Okay, max. Where I will write this max? I will write this max here. And this is the curly bracket starting here, ending here. And then minimax into n1. Okay, I can write, I am writing this minimax with mmax. Okay, mini m and m. I am writing it shortly, yeah. And then the bracket, and then the bracket. This is for the n1. And then comma, and here I am writing again m. This is for the n2. Similarly, m, and this is for the n3. Now this whole statement is done. And here we are calling minimax algorithm again with the new node n1, n2, n3. Huh? And as in this algorithm, we have to follow the depth first search. So that's why I will calculate this one first. Depth first search. So I will calculate this node first. So, okay, now this, it will call this minimax again with n1. So now my this n is what? N1. And here I am checking my n1 is deep enough. No, it is a terminal node. No. Then I will come to this else portion. And then here I have to calculate the successors of this N1. So successors of this N1 is these two. So I can call it N11 and I can call it N12. So these are the two successors. So I have now this step is done. And then here my N1 is a min node. Yes, it is a min node. It is a min node. If it is, then else portion will not execute. We will execute this line. And it is doing what? Return min curly brackets. And then, okay, it means that I have to write something here. I have to write min. I have to write min here, curly bracket, and min, and then this curly bracket is ending here. Okay, not the whole level. Okay. So because these are only two successors, n1, n11, n12. So this curly bracket is ending here. Okay. So now this statement is done. This statement is done. And then as I am following the depth first search, so in the next I will call this depth first search, like a depth first search. So minimax with n11, it will call this algorithm with minimax n11, and I will go again here. So it will call minimax with this value, and then I am checking n11 is deep enough. No, it is not a terminal node. This is not a terminal node. This is not a terminal node. Then what? I will come to the else portion. I will calculate the successors. What are the successors? Only one successor, which is this one. N11. I am giving it a new name, N1111. So this is the successor. And then I am checking N is a min node. N, what is my that? N11 is a min node. N11, it is a max node, not min node. It is written here, max. So if it is a max node, then I will come to this line and then I will write something max. I will write something max, and then the curly bracket, and the curly brackets will end. And the curly bracket will end. And here you are calling minimax something like that. So here you are calling with this triple one. And when you call this with this triple one again, here minimax and triple one, and then here you are checking your n triple one is deep enough. Yes, it is terminal node. It is deep enough. So condition 2, return its score. So what is the score? Nobody wins. When nobody wins, the score is 0. You have this information in the algorithm, and you also got this information maybe from here. I told you -1, 0, and +1. So now when you will calculate this value, it would be 0. It would be 0. So return this estimated score. Return. It means the score will be returned and you will go out of this algorithm. So it means that, okay, this minimax will be finished and you will have the value 0. And this you called here in this previous step. This is a minimax. This is the calling of the minimax algorithm. You called it in the previous step. So then this value will go to the previous step. And this is a call to the previous. Now I can remove. This is the max. And similarly, okay, now this value is available here. Just for a moment. The minimax will calculate this value 0 here. And this value this node was a call to this previous method. Okay, this you can understand that this zero value is available also here for this node. But now this node has to decide between these two nodes. So it cannot decide until these nodes on this column will be finished or evaluated or completed. So then algorithm will complete similarly like that. It will call it an N12. It is a min node because now I'm not going into it. You have the idea. So you have the idea. So it will call this minimax algorithm with this value, and it will check it is a terminal node. No, then it will check what are the successors. Okay, these are the successors. This is the next node. Successor mean next node. And then you will call the minimax algorithm again with this node, which is n1, 2, maybe 1. And when you will call the minimax algorithm for this node, it will go again. It will check that it is a terminal node. If it is a terminal node, it will calculate the score. And here you will see the max player is winning due to this line. And when max is winning, the value is what? +1. So that value is written here. That value will be returned to that previous call. And now these two are completed for this node. And this is the max player. So it will get whatever the value you are giving from the terminal node, it will get those values. But from 0 and 1, what value this node will take? This min will decide. Here you can say mm minimax and then n1 and n1. So from 0 and 1, and if it is a max, now I can erase all the values. So this min player will not allow min player is trying to minimize, max player is trying to maximize. So this minimum player will not accept any higher value. It will always accept lower value. So from these two nodes, which has the value 0 and 1, this min player will take the lowest value, which is 0 for this node. For this node. So if it is a depth first search, so it will come first like that. It will, and then it will go back. You can say it is 1 1, so it will go back and then it will execute this one. And then it will go back, then it will go like that. And then here, after finishing it, it will come like here. This is the execution of the depth first search. And then it is finished, then the values will come up and then it will execute this one. And like that, come here, will take the value and then in this way, and finally it will give these values back up to this root node. You know. Anyhow, so now from this branch of the tree, you will have the value 0 at this node. And when the DFS will execute these things, similarly, by using this algorithm is written according to that DFS. But here we have the recursion only. The only difference is we have the recursive step. So then it will execute this one. And here the O is winning. So that's why calculating the value for the terminal -1, which is moving up. And then it will go here. And here X is winning. The value is 1. That 1 is coming here. But from this -1 and 1, min, this is the level for the min. So min will always accept minimum value. So that's why we are accepting -1. -1 value will traverse up here on this node. Similarly, here you can see the value for this. Here O is winning. Here who is winning? Nobody is winning. So that's why value 0. So this value will come here from this -1 and 0. -1 is coming here. And this is the level for the max. Max will always accept maximum value from its successor. So these are the three successors. And what are the values? 0, -1, and -1. and the maximum value is 0, so that's why max will accept 0. So I hope that now you have the understanding of this simple algorithm and also this tree, whatever the values in it. And now, have you any question up to this point? Hmm. Output? Yeah, optimal strategy. Less chance to lose. How these values are selecting from, for example, what is your question? For example, this is the value 0 and this is the 1, huh? And you are saying how this algorithm is selecting between 0 and 1, how this 0 is selecting. This is your question. Here we have not too much advanced rule here. Here we have simply a rule that minimum will accept the minimum value and maximum will accept the maximum value. So we don't have that advanced algorithm here. That advanced strategy will come here in this alpha beta pruning algorithm. So that is the simple algorithm using DFS. So that's why you are not seeing any equation separately here for selecting the best solution, you can say. But here you have to only compare between two, 0 and 1. And that comparison is done by taking the minimum and maximum. When you are allowing that minimum will take the minimum value and maximum will take the maximum value by using this function, min and max, you are comparing. Minimum is taking its own minimum value and maximum is taking maximum value. So basically, you are comparing and taking the minimum. You are comparing and taking the maximum. From all these values, from n1 to nm, why you are taking minimum? So basically, that comparison is implicitly there, by default there. You are looking all these values, and then you are taking only the minimum one. So basically, you are comparing and taking the minimum one. Similarly, here for the max, you have this one value, two value, three, up to m values. And from these m values, you are looking over it, and then you are taking the maximum value. So comparison is there, finding the minimum maximum value is there. So this is, you can say, your optimal strategy in this algorithm, in this simple algorithm. In this simple algorithm, this is your optimal strategy. But this is simple. So that's why you don't have any advanced equation here. You will see this equation in the next algorithm. Yes. These one. Yeah. Normally, for example, this root, you are saying that I am giving now the move to the max. You can change it. You can give the default to the min first. If you will write min here, then the next will become max. You can change. This is not an issue. So you can start with the max or you can start with the min, no issue, because both are players. Any other? Any other question? So now we have another example for the same algorithm. Another example for the same algorithm. And here we will not go into we from our previous practice, we know that how that algorithm is going on, okay? So that's why now we are directly applying that algorithm logically over this example. And for example, if this tree is given to us, and here the root is max, and then the next level is min, and then the next level is max, and then the next level is the terminal node, and the terminal node, and the values are also given. Then what you have to do? Okay, according to the depth first search, you will come here first. You will come here first. You will see these two. You will see these two values first. -1 and 4. The above is what? Maximizer. So this up to this level D, the max player, the maximizer will do what? It will take minimum value or maximum value? Maximum value, because this level, this brown level is the level of the maximizer. It will not accept minimum value, it will accept maximum value. So that's why you are seeing here the value 4 at node D. Similarly, for these two, J and K, E is the level of max, 2 and 6. The maximizer will accept value 6 at node E. If it will go like a depth first search, that depth, after taking this 4 here, the node will go here and then it will come here and execute it, and like that. So that's why, but we are skipping many steps in these diagrams, okay? And here from these two, we will the max this maximizer will accept maximum value. Similarly, from here, when the depth first search will come here on these two nodes, it this max player will accept -3 and -5, it will accept the maximum value. Similarly, from these two, it will accept the maximum value. And now this is the level for the minimizer. This is level for the minimizer. And minimizer will do what? It will accept the minimum value. So that B, now these two are successors of B, 4 and 6 are the values. What is the minimum value? 4. So this B will accept the value 4 here in the next diagram. And similarly, this C from these two successors, -3 and 7, it will accept the minimum value -3 from here. And similarly, in the next diagram, from these two successors, what A will accept from these 4 and -3? 4 is the maximum value. This is the level for the maximizer. So it will accept 4. And this 4 is lying where? This 4 is lying here. So this is the optimal route, you can say. Now, this is easy, huh? Because now you don't have to go into the details of the algorithm, huh? So that's why it's easy. Now, properties of minimax algorithm. 4 properties: completeness, optimality, time complexity, space complexity. We already said that minimax algorithm is like a DFS algorithm. We will execute actually depth first search in this algorithm. Some formulas are different, but the nodes are expanding in this algorithm according to the depth first search. It's the calculation of this algorithm is different, but the expansion of the nodes is according to the depth first search. And if it is according to the depth first search, then its completeness, optimality, time, space would be according to that. According to that. So that's why we are saying complete. At that point, for the depth first search, we said no, it is not complete, because if you have loopy paths in it, if you have infinite state space, then it is not complete. But if you have a finite state space, or if you have a finite search tree, then it is complete. Similarly, optimal, when it is not complete, then you can say it is not optimal if it is not complete. But if the search tree is finite, then it is complete. And then you can also say that it is optimal. Why optimal? Because here in this minimax algorithm, now you have to think in according on this algorithm. Because in this minimax algorithm, min is trying to minimize, max is trying to maximize. Min is trying to minimize, max is trying to maximize. And if these two players will play infallibly, which means if these two players will play without any error, without any error, if these two players will play, then it is optimal. It will give you an optimal result. Time complexity, because it is depth first search, so order of b raised power m. This is the same as DFS. And we discussed this there already. Space complexity is, according to DFS, order of b m. M is the maximum depth of the search tree. B is the branching factor of the tree. Limitations of this algorithm. Limitations. Hmm. Yeah, you can say two player. Limitations of the, because it is following depth first search, and in the depth first search you will have to explore all the nodes from the left to the right of the tree. So then this will make the game, complex games, really slow. For this tic tac toe, it's okay. But if the game is like a chess or the Go, this is Go. You already maybe know what is this game. I don't want to explain it. Here in this game, red is trying to make its own area and the blue is trying to make its own area. This is not my objective to explain this game here, okay? Because we are not discussing anything related to it, but I just mentioned a picture of it. Here you have to put beads on this board. This is a board. You have to put these beads, one is blue, other is red, on the board, and you have to make your own territory, okay? You have to make your own area. For example, here, this, these are the area, open area for the blues. Or you can say, if, and so, sorry, so this is the open area, and these red beads now are prisoners. They cannot move, okay? They cannot move. And the open area, and the open area for the other team, which is this red one, this is also an open area. This is also the territory of red. Okay, this, mainly this is the territory, but you can also say that this is also, so this is something common territory between blue and red. But here the red are the prisoners, because red cannot move anything, so they are gone actually. Only, yeah, the, so here in this situation the blue is in a strong position, okay? You can say in a strong position. Anyhow, so if you have the game like that, then for complex game, this minimax algorithm will not work. For tic-tac-toe or like simple games, you can apply this minimax algorithm. Because, for example, and for the complex games, because complex games normally has huge branching factor. They have in the tree, they have many nodes. There are many branches in the tree and there are many nodes in the complex games. And when you have many branches and many nodes, it means that the players have many options to do many things. And when you have, then the game will become slow. And these limitations, we can improve these limitations of this minimax algorithm by using another algorithm that is called alpha beta pruning algorithm. We will see it from here. Alpha beta pruning. So this algorithm again would be the same concept as you have studied in the minimax algorithm, but there would be some extra things in it. So that's why we are saying that this algorithm would be the modified version of the minimax algorithm. Exponential, we are saying, because here we have something nested into it. This is call within a call. So that's why it is, you can say loop within a loop. So when you have nested loops, then the complexity of those algorithms normally ends here, exponential, okay? And here you have a call within a call. So that's why here we don't have the loops, But the meaning of this call within a call is nested loop. So when you have something nested loop, it is n square or something exponential or n cube or whatever. It depends on the call actually. So that's why we are calling it exponential minimax algorithm. And this is the, so you can call the minimax algorithm with a new name, exponential minimax algorithm. You can call it, no issue. And this alpha beta pruning algorithm is what? It is the modified version of that previous algorithm, of that previous exponential minimax algorithm. What is the difference of this alpha beta pruning and that previous minimax algorithm? The difference is only that alpha beta pruning algorithm prunes or filters the branches of the tree which are not needed to explore. And in this way, this alpha beta pruning algorithm will save the time. And in this way, this algorithm would be faster than the minimax algorithm. So, so what is the difference? The difference is this algorithm will prunes away branches which are not contributing in the decision or which are not contributing in the solution. It will prunes away or it will filters those branches which are not possibly affecting the final solution, which are not contributing in the final solution. It will filters those branches. And when filters those branches, the algorithm will not execute those branches. And in this way, it will take less time to find the solution. And consider here, you have a two ply game tree, or you can say two-player game tree. And we are explaining the idea of the pruning also here within this whole discussion. And look at here, node A, or you can, and this is the move of the max, and this is node A, and then you have node B, C, D, and then you have these terminal nodes, and these are the values for those terminal nodes, values, and this is the move of the main player. Okay, and here we are representing that this is action 1, action 2, action 3, A1, A2, A3, huh? And then for the B, you have B1, B2, B3 actions. For this node C, you have C1, C2, C3 actions. For D, you have D1, D2, D3 actions. These are the actions. Now, after looking over this diagram, now look over here, minimax, and then the root. We said that this algorithm is similar to that previous algorithm, minimax. We said that this algorithm alpha beta pruning is similar to that minimax algorithm, but the only difference is it filters away the branches which are not needed or which are not contributing in the final answer of the game or search tree. So here we are writing minimax, and this is the root. We are passing this root into it. And what will happen? It will happen that according to that minimax algorithm, max, this has the max, so max, so we are writing this max here, max will give us the maximum number, huh? And then you have first node, third, second, and this node. And here within the max, you have this B, and this B is the level of the min, which will get minimum values from this level. So that's why we are writing min, and this node will take minimum values from 3, 12, 8, which are written here. Which are written here. This is written according to that previous algorithm, but written here mathematically. And then, okay, then comma, and then here this max has these three successors, B, C, and D. This is B, this is C, this is D. Okay. This is basically what? This is representing B, this is representing C, this is representing D. And here, but B is the level for the min, and min player will try to get the minimum values from here. So that's why it is written min inside, and then 3, 12, 8 are written here. That it will, this B will take the minimum values from these 3, 12, and 8. Similarly for here, which is for the C, this C will take minimum values from 2, 4, 6, which is written here. And we are not representing 4 and 6 here due to some reason, because we want to give you the idea of pruning here. And we are representing it with X and Y. But we are representing only the 2 here. 2 and the 4 and 6 are representing with X and Y. Actually, we don't need that. And then for the D, okay, D, this whole is for the D, and D will try to get the minimum from here, 14, 5, and 2, which is written here. And now okay, this is mathematically written here. Understood up to this level? Okay, now moving here. The max, this red one, from this whole equation, from these three values, the max will try to get the maximum value. And but here inside we have the min player, and that min will try to give the minimum value. So okay, first the inside will execute first, and from these three values, min will give us the minimum value, which is 3. Clear? And then similarly for min 2 and x, we are not deciding for a moment it, and we are writing it as it is, because we don't know x and y for the moment. We know, but we are writing it as it is to get the understanding of something. Min 14, 5, here all values are clear, so that's why min player will give us the 2. Now, outside is max. Max will initially from, if this is 3, if this is 2, and if this is 2, suppose I am just saying if this is 2, then max will get 3, maximum. Here at the first step, max has the 3 value. When max has the 3 value, this max don't need this 2, it will reject that value. Similarly, but here, when you are executing it at the first, look here. Here from this tree, I can remove all this drawing so that you can see. When the depth first search will execute, it will go here. It will execute this one 3, and then min will not take this 12, then min will not take this 8, and the 3 value will be updated here for this node. So from this node, the player A now knows that 3 is the maximum value which I am getting from this branch only. Max player know that he is going to get this 3 value after executing this branch of the tree. And now the algorithm is executing this branch. It is coming here. It knows that the maximum value 3 I already have. Max already know that the 3 I already have. So then, but he is expecting to get some more extra maximum value. So that's why it is going to execute it. And when it is going to execute it, here it is that move of the min player. C is the min player. Then min will open it 2. This is 2. And when it will execute, this value will go up here at C. But this player don't need this 2. And then what? Max want to get higher value than 3. And then this min player, when this is 2, and if some higher value like this 4 is now coming next, min will not accept this 4, because this is the point of min player. Min player will not give this 4. If you have higher values, min player will not give those higher values up, because this is the point of the min player. And now at the first point, you have the value 2, which this max player Does not need. Hmm? So it means, so here, now look over here. Now come back to this equation. Here max 3, and we are representing this whole thing with z and the 2 again. And z is what? Min 2xy, whatever. So this node will give us the values which would be 2 or less, not higher. Because here, this is the point for the min player. Point for the min player. Min player, after expanding this first branch, min player has the value 2. If some higher value will come, next min will not allow. Min will not allow. So that's why we are saying here, from this min to xy, you will get either 2 or less, not higher, due to min player. But so 2 or less. So what values you will get up to this node? 2 or less. And if you will get only 2 or less value from here, this player does not need. This has already higher value. So that's why after opening it, there is no need to open these branches. There's no need to open these branches and wasting the time there. So then the algorithm will find these branches automatically, smartly. It will detect these branches and then it will leave. And it will not execute or explore these branches, okay? And then it will save the time. And this is just a simple example how it will prunes away the branches. So this is simple example, but we will discuss this in detail with two examples, this one and this. Then we will understand this algorithm, and then we will go on to this algorithm detailed example in the next lecture. So I will start next from here. Okay, take this also, because this is not a big thing. It's a similar thing. You can here we are saying that you can apply this minimax algorithm for multiplayers. Okay, you can apply this minimax algorithm or this coming alpha beta pruning algorithm for more than 2 players. And if you are going to do that, then here we are using only one value, and that value can be the max for the max, can be for the min. And but if you have 3 players, then you have to use 3 values on each node. So that's why you are seeing these 3 values here. And here we have 3 players, A, B, and C. And this first value is for the A, second value is for the B, third value is for the C on each terminal value. And how you will decide how these values will move up? The triple with high value will move up in the tree. The triple with high value will move up in the tree. For example, here, when you are here, this is the level for the C player. C player has this value, last one. 6 is bigger or 3 is bigger? 6 is bigger. So then this triple, this is the higher value, this will move up. Similarly here, this 2, this is, and this is 1. I'm looking only for the C player. 2 and 1, this is higher, this triple is higher, so this will move up. Similarly, for the C1, C2, so this triple is higher, so this will move up. Similarly here. And but here now it is that move for the B. Now you have to see the value of the B. So this is the value of B2 and 1, which is higher. This one is higher, so it will move up. Similarly, you can apply the same concept here. And then here the player is A. So now you have to look over the values of A. This is A. This is higher, so that's why this value will move up. So this is not different. Next, we are going to, in the next lecture, we are going to start the alpha beta pruning algorithm. And in that pruning algorithm, we will have two variables, alpha and beta. And alpha is the variable that we will use for the max player, and beta is the variable that we will use for the min player. And if alpha we will use for the max player, then we will try to find the best value, which means for the max, highest value. And if beta is for the min player, then we will try to find its best value, which would be lowest value, minimum value. So the highest value for the, and the initial value for the alpha would be minus infinity. Initially, the value of alpha would be lowest value, and then it will try to raise its value up to the maximum. Huh? And then the variable beta, which is for the minimum min player, the initial value would be positive in infinity, maximum value, which then the algorithm will try to minimize. We will see its detail in the next algorithm with this example in the next lecture, inshallah. This is section 2704 maybe, huh?